This is part 2 of section 1.7, Symmetry and Graphs. We're actually on this page of our notes. So we're going to come back to this notes page and finish off the rest of these examples. First, I'm going to show you just a brief review of what we already talked about in part 1 with reflections and symmetry. Okay, so to recap symmetry that you're going to see, when you have symmetry with respect to the x-axis, the points x, y are reflected to create x comma negative y, and they're reflections across the x-axis. When you have symmetry with respect to the y-axis, the point xy becomes negative xy, so those are mirror reflections of one another across the y-axis. And when you have symmetry about the origin, xy becomes negative x, negative y. So this is a reflection across the origin, which is also, to create a reflection, you can think of it as over the x-axis as well as the y-axis, or starting with the y-axis and then to the x-axis. Okay, now when you test symmetry algebraically, you're going to test with respect to the x-axis. So when you have to ask yourself basically, does f of x equal negative f of x? In other words, what you're going to do algebraically is replace the y with negative y in your equation, and then if you get a true statement, so you get the exact same original equation, that means it's symmetric with respect to the x-axis. So if you're checking to see if something, a function or relation is symmetric with respect to the y-axis, you test, does f of x equal f of negative x? In this case, algebraically, you replace the x with the negative x in your equation. If you're testing with respect to the origin, you want to test, does f of x equal negative f of negative x? So this time you're going to replace both the x with the negative x and the y with a negative y to see if your resulting equation is equal to the original. Okay, so I talked about, I think I skipped this in the notes in part 1, so you make sure you understand this part as well. If something is symmetric to the y-axis, then we say that that's an even function. Okay, so here's a picture of an even function. Notice that f of negative x is reflected across the y-axis, so f of x becomes f of negative x. There's the reflection across the y-axis. We call that even. When something is an odd function, then it is symmetric with respect to the origin. Okay, so a picture of that would look like this. Notice that f of x is reflected to give you negative f of negative x. There's actually a negative sign missing right there, and let me put that in there because it's missing right now. I should say negative f of negative x. Guys, stop. Hold on one sec. Okay, now sadly, the x-axis is not even or odd, so it cannot, if something is symmetric with respect to the x-axis, it's neither even nor odd, so it's kind of boring. And that's basically a review of symmetry. So you want to make sure you know what these algebraic tests are. Tank, stop. Okay, now that we just talked about the reflections and symmetry, I want to start with this calculator example. So you're going to need your calculator out right now, so go ahead and get it. We're going to type this function into our calculator. Okay, so I already went ahead and graphed this. I plugged it in. I'm going to hit graph here, and I'm in the standard viewing rectangle, so remember, go to zoom 6 so that you're in the standard one. And this graph isn't great, I can't really see much, but I want you to take a look at this here. Tell me whether or not you think you have symmetry with respect to the x, y, or the origin. Okay, so is it symmetric about the x-axis, the y-axis, or the origin? Now, since this isn't a great picture, let's go ahead and change our window. And let's do that real quick. I'm going to pause. Okay, so I went ahead and I changed my window, and I'm going to graph. Okay, now I'd like you to take a look at this, and again, now that it's a better picture, it's a little bit better picture. Ask yourself if it looks like it's been reflected, or if it's symmetric about the x-axis, the y-axis, or about the origin. So it looks to me like it's not reflected, over the x-axis or the y-axis. If anything, I would say that it's probably a reflection and it's symmetric about the origin. So what I'm going to do is now test that algebraically. Okay, so we want to test algebraically whether or not this function here is symmetric about the x, the y axis, or about the origin. So let's test. Remember, if we want to test if it's symmetric about the x-axis, we need to replace y with negative y. Oh, the reason why, I should explain this too, just because it looks like it's symmetric on a picture or a graph doesn't mean that it's necessarily symmetric, about anything. So make sure you're always verifying algebraically. So our test here to check whether it's symmetric about the x-axis, remember you want to check, does f of x equal negative f of x? In other words, replace your y with negative y in your original function. So if I do that and I replace this here with a negative y, I end up with this, and I always want to solve back for y. I would divide that out, and I'd end up with negative x cubed minus, or 1 over negative quantity of x cubed minus x. So clearly this is not equal, so no, it is not a reflection or symmetric about the x-axis. So let's test next if it's symmetric about the y-axis. So for this we want to check, does f of x equal f of negative x? In other words, let's replace x with negative x. So we take that and we plug in for x, negative x, and I'm going to simplify. So I have y equals 1 over, this is negative x cubed plus x, and again, and I can actually factor this just in case you're not totally certain about this one. This is clearly not our original function up there. I didn't quite make it up there, but it's not our original function. Alright, so the last test, so this is not symmetric. The last test is going to be whether or not it's it's symmetric with respect to the origin. So we're going to test, does f of x equal negative of f of negative x? So in other words, let's replace x with negative x and y with negative y. Now when we test this, I have negative y equals 1 over negative x to the third minus negative x. And I'm going to simplify. So I have 1 over negative x cubed plus x. I'm going to divide or multiply by negative 1, however you want to think of it. And I end up with y equaling 1 over this, which is going to simplify to 1 over positive x cubed minus x. So you can see that this is indeed the exact same as our starting equation. So this is symmetric. Why can't I say that right? Symmetric with respect to the origin. Okay? Alright, so that's how you would verify algebraically, but you can see also from a picture how that would look. Alright, next we're going to move on to circles. Okay, so here you probably remember a little bit from geometry. I think you probably would have worked with conics a little bit in 90-91. But I have the equation of a circle here. HK represents your center, and R is your radius. Okay, so this is the equation, the general standard form for an equation of a circle. Alright, so the very first question on here is actually more difficult than the second question. But we have the we're supposed to find the equation and graph a circle with endpoints of -4, 1, and 0, 5. Alright, so let's just kind of sketch this out. I do have a graph provided, but even if you didn't, you could just kind of sketch it, do a rough sketch. And okay, so here are my 2 points. If this is a diameter, the endpoints of a diameter, that means that the center is obviously the midpoint of that those 2 points. Now we also can figure out the radius by finding the distance between those 2 points and cutting it in half. So I'm actually going to do that first. I want to find the distance here. So the distance between those 2 points. So the distance between those 2 points is going to be found by taking the absolute value between -4 and 0, which is 4, squaring that number, plus the absolute value between these two numbers, 4, and squaring this number. So we get 16 plus 16, root 32. Okay, so that simplifies to 4 root 2, which means that this is again the overall distance. That's the diameter's distance. So the radius is actually 2 root 2, because it's half of the distance of the diameter. Okay, next we need to work on finding the midpoint between those 2 points to find the center. So to find the center, we're going to use midpoint formula. And recall that midpoint formula is the average of your x coordinates and the average of your y coordinates. Okay, so we're going to take -4 plus 0, cut that in half, and 1 plus 5, cut that in half. We end up with the point -2, 3. So my center is at -2, 3. Oops. There we go. And my radius is at 2 root 2. So now I'm going to plug that directly into my equation, general form, x minus h squared plus y minus k squared equaling r squared. So hk, we're taking the opposite of h, so when we plug this back in, it's going to become plus 2. So x plus 2 squared plus y minus 3 squared is going to equal 2 root 2 squared. So I'll do that real quick. That's going to be 4 times 2, give me 8. Alright, so that's the equation of a circle. I'm actually going to come back and manipulate this equation when we want to graph it. So let's go back to our graph real quick and try to graph this. So my center was at negative 2, 3. Alright, now normally, like if you were to get a nice even integer for your radius, you could just graph up, 1, 2, 3, 4, whatever, plot your points, go up that amount, down that amount, right that amount, left that amount, and then draw as best you can a circle. But here we don't really have a nice integer, so you're going to have to just sort of estimate the value for 2 root 2. So 2 root 2 is between the number 2 and 3. It's closer to 3. So I'm just going to kind of estimate and go 1, 2, a little bit past 2.5 and put my dot here. I'm going to go left of the radius, or of the center, put my point here, down here, and to the right about there. So it's a ghetto looking circle, but I guess it'll do. Okay, next question. A circle is tangent to the lines y equals 2 and y equals 8, and the center goes through the line x equals 5. We're going to find the equation for the circle. Let's see if I can get the whole picture in there. Okay, so just a review real quick of geometry. If a line is tangent to any shape, that means it touches it exactly at once. So that's what point of tangency looks like. So again, you might want to just sketch this roughly, especially when you're doing homework or you have a test or a quiz. You're going to want to just have a rough sketch so that you can kind of see what the problem is asking you to do. Okay, so my computer's going berserk. Okay, let's graph y equals 2 and y equals 8. 6, 7, 8. Alright, so the circle is tangent to both, which means it must lie inside here, right? And it's got to touch both the both lines. The center goes through the line x equals 5. So there we go. Alright, so the center must lie on this line, which means the x-coordinate has to be 5. That's basically what they're telling you here. Now, even though you don't have like points, coordinates, you do know that the midpoint is going to be where you find their center. So basically the halfway point between these two lines is going to be the center of your circle. So you're going to need to find the overall distance between these two lines. And the distance between these two lines is obviously 6 units. So we cut that in half, and our radius is 3. And if we want to find the midpoint, we know that the x-coordinate has to be 5. We also know that if the radius is 3 units, that means that it's it's exactly 3 units away from this y-coordinate and 3 units away from this y-coordinate, which places it at 5, 5. Okay, so the y-coordinate here is 5, the x-coordinate is 5, which makes it kind of confusing, but there we go. So that's our center. Alright, now we just said that what the radius was, so we're just going to plug in our center and our radius. So x minus 5 squared plus y minus 5 squared is equal to our radius squared, 9. Alright, now to graph this, this is a little bit easier, like I said. We're just going to go up 3, up 3, down 3, and there's our beautiful circle. A little bit better. Alright, now this little note down here, I just couldn't fit it somewhere else, but I wanted to put this on here because whenever you graph on a calculator, you have to get, if you go back to your calculator here, your calculator is always in, why isn't it showing it? Whoa. Your calculator is always in y equals form, so you have to get the y by itself in order to do that. So in this case, if I wanted to isolate the y, I would subtract over the x minus 5 squared term. So that would leave me with y minus 5 squared equaling negative x minus 5 squared plus 9. And then I would want to take the square root of both sides to try to isolate this term here and this expression in the inside. So I take the square root of both sides, and I'm left with positive or negative. This is super important not to forget this positive or negative. So positive or negative of negative x minus 5 squared plus 9. Okay? Now I'm going to add over the 5, and I have this. Now in your calculator, your calculator can't read this. You actually have to input it for two different functions. So you would input this as y equals 5 plus the square root of negative x minus 5 squared plus 9, and y equals 5 minus, I'm running out of room, but you get the point. So also make sure that to set your window with zoom 5, because you want to have an accurate picture of what it looks like. Otherwise it'll distort the image. So you want to see that it's a circle, so hit zoom 5 because it'll make the whatever viewing rectangle you're in, it'll make it a square. So I'm going to show you guys real quick. I'm going to pause it and then input that, and then you can see what that would. Okay, so as you can see, I've only inputted the one expression or one equation in here, one of the functions y equals 5 plus the square root. So let's take a look at what that looks like. You can see that it's only graphing the top half of that circle. Okay, so it's only got a semicircle here because you still need the bottom half, right? So let's go back, pause, go back, and then okay, so I inputted the second half of it, and when I go to graph this, that looks pretty weird. So I don't have it in the square. I'm going to hit zoom 6, or sorry, zoom 5, and it'll automatically readjust my window for me to make it look more like a square. And you're going to see that, oh geez, what is this? It's missing little parts. Don't worry, your calculator just can't, at that point, graph it without making it look like a straight line, so it just doesn't graph it at all. So it's a calculator thing, don't worry about it. That is the correct graph for the equation of this circle. Alright, thanks for hanging in there. We're on the last part of this lesson, and this is a pretty important algebraic part, so if you understand after doing one how to do this, then I would try to finish the rest of those, pause the video, finish the rest of them, and then don't even listen to the playback. Check your answers with the answer key. If you get them wrong, then go back and try to figure out what you did wrong. Alright, so when you're completing the square here, the reason why you're completing the square is right now this is actually the equation of a circle. It's very funky. It's not really easy to see that it's a circle. So what we're going to do is rearrange this and write it into standard form. So what you're first going to do is move your constant term just like you normally would if you only had one variable. Since we have two variables here, we still move the constant. So I'm going to do that, and I'm also going to factor out the lead coefficients for each variable. So in this case, the lead coefficients are the same. So I factor out that, and I have 1/2 x here, and 16 times y squared minus 4y. Notice I'm not taking out a GCF, it's just the lead coefficient, and move that 15 over to the other side. Alright, now I take, if I want to complete the square for the x term, I take half of this middle term, so that's going to be 1/4, negative 1/4. I now square that number, and I get positive 1/16. On the other side of my equation, in order to balance this, I need to add back in 16 times 1/16, because that's what I'm actually changing this equation by. So I need to balance that out on the right-hand side and add 1, because 16 times 1/16 is 1. Alright, now I do the same thing for the y term. So I cut that 4 in half, which is going to be a negative 2. I square that number, it's positive 4. Alright, so I actually added here a factor of 64 onto the left side, so I need to add 64 onto the right. Alright, now I'm going to rewrite this as 16 times x minus 1/4 squared. And the reason why I know it's 1/4 is because that's the number that I took in half, right? I took negative 1/2, and I took that in half and got negative 1/4. So I know that that's what that number should be. Plus 16 times y minus 2 squared. Remember when you cut that in half, that was 2. And then equals, on the other side, 80. Did I add that right? Yeah. Okay, so now we're going to divide out this term. If it's a circle, these terms should be the same. If you remember from conics at all, if they're different, then you could have a hyperbola, you could have a bunch of different stuff, an ellipse. But for right now, we're only working with circles, so these should be the same coefficient. So we divide that out, and we're going to be left with the standard form. Standard form for a circle. So it looks like here your center is at 1/4, 2, and your radius is √5. Okay, so I think I actually changed this one and solved for the y here as well. So you can check that with the answer key just so you know how to input that into your calculator as well. Alright, the second problem here, a little bit different because there is no x squared term, or a linear term for the x. So I still move over the 18, but that 3x squared is going to kind of be on its own. So I have 3y squared plus 6√2y equaling positive 18. So I'm going to leave alone that 3x squared because there's no linear term here. I'm going to factor out that 3, and I have 2√2y. Alright, so now I'm going to complete the square. The only term I have to do that for is this term here. So remember, I take half of this middle linear term, and that's going to be, if I cut that in half, √2. Now I need to square that number to get the number 2. So that's the term I'm going to add in here. So I have 3x squared plus 3 times y squared plus 2√2y plus 2. I'm going to show the workout there on the side for it, just in case you need to see it. So I cut that in half, and then I squared it. And inside that cancels out, leaving me √2 squared, which is why I have 2. So remember to add a factor of 6 onto the other side, not just the 2, because you have to multiply 3 times 2. And it's 6 over there. See, now we have 3x squared plus 3 times y plus √2 squared. And remember, this term here is always going to come from whatever your middle term was when you cut it in half. Alright, now on the other side I have 24. And now I can divide out the 3, right? These terms here will divide out. I'm left with x squared plus y plus √2 squared equaling 8, which means now I have a center of 0, negative √2, and a radius of 2√2. So I just take the square root of this, remember this is r squared, which is why I end up with 2√2. Alright. I also believe that I solved for y so that you get, your two cases to put into your calculator here. So check that if you want some extra practice. Alright, last one. So here we're going to complete the square and derive the quadratic formula. So we did this on our quiz. I just want to do it one more time with you guys. So I'm going to do the check first for this. So I already know what the quadratic formula is. I have that memorized, right? So I can check to see what my solution should be. So the quadratic formula states that x should be the opposite of b, and in this case b is already negative, so it's going to be positive b plus or minus the opposite of b squared, which is still just positive b squared, minus 4 times a times c, and in this case c is 2, divided by 2a. So I should end up with, after I derive the formula here, completing the square, after I derive it, I should end up with this. Okay? So let's derive. Okay, so the first thing we always do when completing the square, we move over the 2. Next thing we do, we always factor out the lead coefficient for the quadratic term. So that lead coefficient is a here, so we factor out that a, which means you're left with b over ax. Alright, now we're going to complete the square. We're going to take the linear term, we cut it in half. So if we took that linear term, we cut it in half, I get negative b over 2a. Then I have to square that term, and it ends up being b squared over 4a squared. Okay? So let me start. I'll just leave that little side note here. So now I have a times x squared minus b over a x plus, right, because you're squaring that, it becomes positive b squared over 4a squared, equaling negative 2. Now, when I balance the equation, again, you want to make sure that you're multiplying a times this, and you multiply a times b squared over 4a squared. One of those a's is going to cancel, and that leaves you with b squared over 4a. So I'm adding now b squared over 4a to the right-hand side. Alright, again, I'm going to leave that little side note, so I'm going to shift over here. Okay, now I'm going to rewrite that and factor it, so that's x minus, and remember this middle, or this term here, should always be half of that linear term that you had before, so we're going to take b over 2a, so x minus b over 2a squared is the factored form of that. And on the right hand side, I'm going to work on making sure that I can write this as a single fraction, so that changes that negative 2 into negative 2 times 4a over 4a. So I simplify that, and when I add that together, I get negative 8a plus b squared over 4a. Okay? Now on the left-hand side, let's keep that the same for right now. Alright, now I want to get the x by itself, right? So the next step is to get rid of this a term here. So I'm going to divide out the a term. When I divide that out onto the other side, I'm going to change that to a squared, right? So I'm dividing it, it's going to end up in the denominator. So I have x minus b over 2a squared equaling negative 8a plus b squared over 4a squared. Alright, now I take the square root of both sides so that I can further isolate that x. And I have x minus b over 2a equaling, on the right hand side, again, positive or negative. Now the top of this, the numerator here, is really, really messy to try to take the square root of. So I'm going to keep it underneath that square root. However, the denominator, the square root of 4a squared, is just 2a. So now the only thing left to do is add the b over 2a. So add that to either side, and we now have something that's pretty similar to what we derived at the beginning, or what we used when we used the quadratic, what we got when we used the quadratic formula. So I'm just going to rewrite this a little bit differently. Since they do have the same denominator, I'm just going to put the numerator all together, and then I'm going to switch this and make that b squared minus 8a all over 2a, and let's see if this actually matches. So I have b plus or minus the square root of b squared minus 8a over 2a, which is the same thing we got here. Yay! So you guys can always check to see if you got them correct by just quickly putting it into the quadratic formula. And that is the end of a super long lesson. Thanks for hanging in. Bye-bye.